Okay, so last time we were together, we talked about what was called a one-to-one function. And just to refresh your memory, a one-to-one function it's a function. So that means each x has a single y value. And then in addition, that y value is unique. So that's what it means for something to be one-to-one. And the reason we cared about one-to-one functions is because their inverses, meaning when I flip-flop the x and the y values, the inverses of a one-to-one function are also functions. So that's their utility to us. That's why we care and are going through this process. So what we're going to do now in section 6.2 is we're going to get a new basic function. It's going to turn out to be a one-to-one function. And that's why we've waited until this point to go ahead and introduce it. And so we're going to talk about what's called exponential functions. And what makes something an exponential function, and something that we haven't seen yet this semester, is in an exponential function, we are going to see that the variable is in the power. So when we're working with these, we're going to notice that the variable for the exponential function is in the power. So what I'm going to do in example 1 is I'm just going to show you how to real quick graph an exponential function. It's basically, we're just going to make a little table. The thing that changes, you'll notice from my example 1 to exercise 1 is the different bases, and we're going to see how the different bases change the look of my exponential function. So what we're going to do together here is we're going to graph the function f of x is equal to 2 to the x power. So you can clearly see the x, the variable that is in the power. So off to the right, I'm going to make a cute little table right here. Here's my xy table. And I'm just going to put in some values so that I can get the feel for the shape of what the exponential function is going to look like. So just to make sure we're comfortable calculating powers, I'm going to start with 4. Maybe that's a little too big, but that's fine. 2, 1, 0, -1, -2, and then we'll stop there. There's not much use going beyond that because the numbers are going to get small. So I'm expecting that everybody's fairly comfortable taking things to powers, but let's go ahead and see. So 4, when I put 4 in, so just to make note, if you need to write this down, great. If you don't, great. So what that looks like is I have 2 to the 4th power. And what is 2 to the 4th power? What does your calculator tell you when you take 2 and multiply it by itself 4 times? 16, perfect. Okay, 2 times 2 times 2 is 16. And so the next one, when I put 3 in, 2 to the 3rd, 2 times 2 times 2 is going to be 8. To the 2nd, 2 to the 2nd, 2 times 2 is just going to be 4. 2 to the 1st, 2 to anything to the 1st power is just itself, so 2. 2 to the 0 power. Thank you very much. I was just going to ask that question and make sure that we remember that. It's always kind of a forgotten bit of trivia. 2 to the 0, anything to the 0 power is 1. Remind me, I know it's been a long time since intermediate algebra. What do negative exponents tell us? No one remembers negative exponents? Maybe you do, and I know it's been a long weekend and you're tired, you're out late partying last night for Halloween. And so 2 to the -1, what a negative exponent tells us is that the base is in the wrong place. And so what I have is 1 over 2 to the 1st power. Okay, that's the property of negative exponents. If you need a video on that, I went through it with my intermediate algebra. I can share. If you need more of the Perkster, I can share a video and you can watch more. Okay, 1 over 2. And then the last one, 2 to the -2 power. Well, what's going to happen there? Let me write this out since we seem to be a little shy about our negative exponents. That's 1 over 2 to the +2 power, and 2 to the +2, that's 4. So that's 1 over 4. There's my values. So I got plenty of values. I'm going to get a really good feel for the shape of this exponential function. You'll notice I picked the 4 intentionally. I knew it was going to be too big for our graph, but I just wanted to practice making sure we had power. So 4, it's way up at 16. It's off my grid. I'm not going to bother plotting it. When I put in 3, I got 8. So over 3 and then up 8 and make a dot right here. 2, 4, so I go over 2 and up 4, make a nice dot right here. 1, 2, over 1, up 2. 1 or 0, 1. What you notice here with an exponential function is notice the gap between my y gap between my successive x values gets bigger and bigger. Here the gap is 1 unit, and then going from this point to this point becomes 2 units. This point and this point it's 4. If I was able to plot 16, it then the gap jumps to 8, and that's what's happening in an exponential graph. As I go to the right on this, it is getting bigger faster. Okay, it's rate of increase. If you take calculus, all sorts of fun things happen with exponential graphs. Okay, -1.5, so I'm just going to go there, and then -2.25, so something small and like that. So my graph looks like this. In some contexts, if you're like in an economics class or a biology class, they might call this a J curve. It's called an exponential growth curve. If you like, we're just going to call it an exponential function. One thing to notice here is that since my base is 2, 2 to any power is going to have a value. I'm never going to get 0. I'm never going to get anything negative. So what we have, the x-axis functions as a horizontal asymptote. Okay, so I'm just going to make a light dotted line here, and I'm going to put the initials horizontal asymptote. The graph never goes through the x-axis. What's the domain of this graph? What's the furthest to the left this graph is going to go? Perfect, thank you very much, -infinity. And then what's the furthest to the right this graph is going to go? Yeah, it's going slow. The y values are increasing so fast, but yeah, you can put in any value for x, and you can take 2 to any power. It's going to get very large, very fast. And so all real numbers is the domain of this graph. How about the range? What's the lowest down this goes on the y-axis? Yeah, 0, but like I just said a minute ago, 0 is a horizontal asymptote. It's never going to equal 0. So I'm going to put a parenthesis on that end, not a bracket. And then you can see quite clearly, this is probably the most obvious one of the 4 questions, is that it's going up to infinity. A blast from the past question that we asked a long time ago in chapter 2, is this function increasing or decreasing? Yeah, it's increasing. Remember, increasing means as I go from left to right on the x-axis, what's happening to those y values? Well, as I go from left to right, the y values are getting bigger and bigger and bigger. So this is increasing. I'm going to circle the word increasing right there. And then the last thing I'm going to point out to you before I have you do your exercise, and the reason that we're mentioning this here is that it passes the horizontal line test. This is a one-to-one function. So that means when we go to start talking about section 6.3, probably at the end of today, I'd like to get a chunk of the next section in. We're going to be able to talk about the inverse of this function. I know you're super excited about that because you seem to be super excited about everything this morning. So I love it. All right. So what I would like you to do, please, is using the template that I just created for example 1, I would like you in exercise 1 to graph 3 to the x power. All right, so I'm just going to get started. If you're working, keep working. If you don't understand something going on here, let me know. Exponential functions. This is the topic of kind of the rest of, or a bunch of the rest of this unit. So I'm going to put in 3, and so when I have 3 to the 3rd power, that's 3 times 3 times 3. That's 27. So clearly, I did that intentionally just to show you, clearly that's not going to fit on my graph. And notice what happened when I changed my base. We just did base 2, and when I put in 3, 2 to the 3rd, 2 times 2 times 2 was 8. Well, 3 to the 3rd now is 27. This is getting bigger much faster. Just by increasing the base one whole number value, I have created a function that's increasing by orders of magnitude over the previous one. Okay, 2, when I put in 2, 3 to the 2nd, or 3 times 3 is 9. 3 to the 1st is 3. 3 to the 0, anything to the 0 power is 1. And then 3 to the -1, remember that negative exponent, 3 to the -1, it means the base is in the wrong place, so I have 1 over 3 to the 1st, or just 1/3. So now I'll plot those points. I'm not going to plot 327 because I'd have to write on the desk. So now 2 and 9. So 2 just at the top of my grid. 1 and 3. 0 and 1. -1 and 1/3. If you put in -2, you got a 9th. So you've got something even smaller. And so here's what my curve looks like. It's dropping down, just like this. Again, we've not moved this around at all, so my x-axis is a horizontal asymptote. You don't have to do this dotted line. I'm not super concerned about that, but what I am concerned about is you understanding that this graph does not go through the x-axis. Okay, that's one of the things I look for when I grade your test is, did you treat the x-axis as the asymptote and like you're supposed to? So again, the domain range, I asked you for the same sort of questions. The domain, that doesn't change. It's -infinity to infinity. The range doesn't change. It's 0 to infinity. Okay, it never, again, there's a parenthesis at the 0 because it never goes down and hits the axis. It just gets closer and closer and closer and closer and closer to it. And then again, we have what's called an increasing function. I'm going to circle the word increasing because as I go left to right along the x-axis, the y values get obviously bigger. Before I have you do the next one, is there any question, anything going on in your brain that we need to discuss? All right, well, the next one's super fun. You're going to love it. I've changed the base. Now the base is not a whole number. It is a fraction. I want to see what that fraction does. I'm going to make a suggestion to you on what you should use for your values for the fraction. So your XY table, just going to give you a little suggestion here. I recommend that you use 2, 1, 0, -1, -2, and if you feel like it, -3. So give it a try. Probably the hardest part of this is scraping the rust off that intermediate algebra knowledge on what to do with negative exponents. I don't think plotting the points is super hard, so give it a go. All right, I'm going to start calculating some powers. If you need me to explain something, please let me know. That's why I'm here. Otherwise, a computer could just go ahead and teach this class. So when I put a 2 in, I have 1/2 times 1/2, and so that's going to be 1/4. When I put 1 in, I have 1/2 to the first power. Anything to the first power is just itself, so that's going to be 1/2. When I put 0 in, anything to the 0 power, doesn't matter if it's a fraction or doesn't matter if it's an integer, anything to the 0 power is going to be 1. -1, so let me just write down this first one. When I have 1/2 and I'm taking it to the -1 power, well, remember, the -1 means my base is in the wrong place. It means I got to take the reciprocal, and so that's the same thing as 2 to the first power. Okay, so that becomes 2. And the same thing for -2. I'll go ahead and write down another one just because I feel like it. So I've got 1/2 to the -2. Well, again, the negative tells me I've got to adjust the base. So instead of 1/2, I'm going to have a base of 2 to the second. So 2 to the second becomes 4. And so when I put a -3 in, 1/2 to the -3, again, that negative tells me I've got to flip my base. And so I have 2 to the third, or 2 to the third is 8. Okay, those are the values. Again, that's probably the hardest part to this problem is doing that. So now I'm going to go ahead. I'm going to go over 2. I'm going to go up 1/4. So just a wee little bit right there. And then over 1, up 1/2. 0, 1. -1, I go up 2. -2, I go up 4. And -3, I go up 8. So those are very similar values as when the base was 2. I'm not going to put the dots for the horizontal asymptote on this one. I don't want to mess up the graph too much. There's only really one huge difference in these questions that I've asked at the end. The domain is the same, -infinity to infinity. That hasn't changed. The range is the same, 0 to infinity. What has changed about this graph now? What's going on with this function as I go from left to right? It's now decreasing. Yes. Awesome. Good. Good to note that. And so because of that, I need to let you know about this property of exponential functions. Okay, so this property is this. For the exponential function, f of x is equal to a to the x. And just a couple notes about this function as we go through this chapter. We are not going to consider any bases that are negative, so a is always going to be greater than 0. And also because it's not super interesting, we're not going to consider the value 1, okay, because 1 to any power is just going to be 1. It's just a horizontal line, so it's not super interesting. So for the exponential function f of x equals a to the x, we note the following, and you just noted this in these examples. If the value of a, meaning if the value of my base is bigger than 1, then a to the x is an increasing function. And then if if a is bigger than 0, because again, we're not considering anything less than 0, that's a different type of function for a different math class, much beyond our scope. But it's less than 1, meaning it's fractional, like 1/2 or 2/3 or 1/5 or something. So if you've got a value between 0 and 1, then a to the x is a decreasing function. So that's the introduction to exponential functions. We're going to keep working with them. So what I would like you to do next is as you flip to page 2, I'll keep this up here for another moment. I'm just going to flip over to page 2 for a minute. The next exercise, what we're going to do now is we're going to combine our new exponential function along with our translations and things that we've been doing since the second unit. Okay, so now that we've introduced the exponential function, these next 3 problems have no new information. What I would like you to do is exercise 3. I'd like you to take the basic 2 to the x function. That was our very first example. And then I'd like to know what 2 to the x minus 4, what that's going to look like. Okay, so I'm going to come back over here in case you weren't finished writing down these properties of the exponential function. And meanwhile, you're working on exercise 3, please. Okay, so all I've done here on the graph is I've reproduced the basic function from the front page. Okay, so all this is a representation of 2 to the third power is 8, 2 to the second power is 4, 2 to the first is 2, 2 to the 0 power is 1, 2 to the negative 1 power is a half, 2 to the negative 2 is a fourth. So that's just the basic function. What does this minus 4 now do to my graph? Just like it's been doing all semester, when you subtract something or add something to the function itself, this is a vertical translation. So this is going to move the whole thing down 4. What I'm going to do, just to as a point of reference, I am now going to move that horizontal asymptote down so that I can see it and so that I don't accidentally go through. So I'm moving basically the x-axis down 4. So there's my horizontal asymptote. And now I'm just going to drop those basic points down 4. So instead of 8, I'm going to move this down 1, 2, 3, 4. Instead of 4, I'm going to drop it down 1, 2, 3, 4. Instead of 2, I drop it down 4 to negative 2. Instead of 1, I drop it down 4 to negative 3. Instead of a half, I drop it down 4 to negative 3.5. And then instead of a quarter, I drop it down really close to the horizontal asymptote. And here is my new graph. It's just the translation. Again, no new information on that problem. We're still getting used to the exponential functions, but now I'm doing my translations that have been following us along the whole semester. Before I move you along to the next problem, do you have a question? Anything going on? I know this is tough stuff, everybody, and I know it's late in the semester. Please interact with me. I get the difficulty in learning this. All right, well then we're just going to slide down to exercise 4. Exercise 4 is based again on a graph we already did on the front page. So you can go back to the front page and look up those basic points, or you can try your best to recollect. So now this translation is based on 3 to the x. So in this one, I've again reproduced the 3 to the x graph. So again, at 2, 3 to the second is 9, 3 to the first is 3, 3 to the 0 is 1, 3 to the negative 1 is a third. And what does the -2, when it's up attached directly to the x, what is the -2 doing to this graph? Right 2, yes, it's going in the positive x direction 2 units. So I'm going to move each of these points 2 units to the right. So just like this. My horizontal asymptote does not change this time because I've not moved it up and down. So I'm just going to let the x-axis function as my asymptote. And you can see here's my graph again, just been translated. It's not been stretched out or anything. So there we are. I got one more of these, again, just reminding us we're keeping these fresh in our memory, these translations and things I can do in my graph. The last example is exercise 5. It's based on the graph of 1/2 to the x power. This time, though, I've thrown a negative out in front of it. So we're multiplying by -1. So see if you can remember what that's going to do to my graph. Okay, so the negative out in front of this one. Anybody remember what is that going to do to my graph? Yeah, it's going to flip across the x-axis. And the reason why, in case you couldn't verbalize that, is because I'm taking all the y values. I'm taking all those 1/2 to the x values from the previous graph. And what am I doing with all those y values? Times by -1. Yes, exactly right. So instead of +8, this value is going to now be -8. Instead of +4, this value is -4. Instead of +2, -2. +1, -1. +1/2, -1/2. +1/4, -1/4. And there we go. Whee! Again, the horizontal asymptote does not change. It is still going to be the x-axis. I'm not going to do it because it's going to make it too messy. So just know that the x-axis here, this is the horizontal asymptote. So again, these were exercises in getting used to doing the exponential graphs. One thing I would recommend is you're going through your homework. I've got some blank graph paper in my office. I can bring it over, or on Canvas, I've linked some blank. Just print out a copy and just re-practice these graphs. Because of the size of the base, these are probably the most common ones you're going to see. Okay, maybe you'll see a 4 to the x, but these graphs get big very fast, as you can tell. So I'm limited in the bases that I can use. Okay, so one other thing from this section, and then we're going to be done with section 6.2, so sort of painless, is solving what our book cleverly calls type 1 exponential equations. And you might be thinking, well, Perkster, what in the world does it mean for it to be a type 1 exponential equation? That's a great question. That would be the one I would ask. What makes it type 1 is that these are equations where we can equate the bases. Later in this class, it's going to be either Wednesday or next Monday. We're going to look at exponential equations where I can't do that. There's a different process, but we don't have the tools yet. We're going to figure out the tool in the next section when we get there. I don't have the tool yet to be able to do that. Now, before we do these problems, I just real quick, I know you know these things, but I also know it's Monday and you were out late last night and you were high on sugar last night because you ate a whole bunch of Milky Way bars. So I just want to review real quick the two of the properties of exponents that you're going to see repeatedly. So remind me, if I have x to the second power times x to the fifth power, what do you do when you multiply the bases? What do you do with the exponents? You add them. And also notice the other thing, the base is the same. If these bases were different, you couldn't do anything. Okay, so what I get is x. I don't change the base at all. And then 2 plus 5, and I'm just going to write that, which would be 7. You can finish that up. That's called the product rule of exponents. Yeah, I don't care if you remember that name or not. I just want you to remember what to do. If I have x to the second raised to the fifth, so I have a power directly raised to another power, do you remember what to do with the exponents in this situation? You multiply them. This is called the power rule. Again, I'm not super concerned about the terminology, but I want you to remember what to do. So 2 times 5, that's the difference between those. So the first one on the left is x to the 7th would be the answer. The one on the right is x to the 10th. Those properties are going to come up fairly frequently as we do this, in addition to that negative exponent property we began talking about. So here is the general gist of how to do this. Notice in example 2, I have 25 to the x is equal to 125. Okay, well, I have no way to know how to solve that. It's not going to be a nice, relaxing answer like a whole number that I could just kind of visualize. So I need a process. So here's your process. What base do 25 and 125 have in common? 5, yes. Okay, so here's what we're going to do. 25, we're going to rewrite 25 as 5 to the second power raised to the x. And 125 is 5 to the third power. And you can use your calculator to get that. 120, I know 125 is an awkward number. You just use your calculator, 5 times 5 times 5, and there you go. We've equated the basis. So what we've done, okay, this is the premise that you are going to employ when you do your examples in a minute. What we've done is we've taken the original bases, and since I could do it, I rewrote them as a base they have in common, in this case 5. So on the left, I'm now going to employ the power rule, which we reviewed just a quick moment ago. And so 5 to the 2x is 5 to the 2 times x power, and 5 to the third, there's nothing to do over there. Now here's the good news. The exponential function is a one-to-one function. We saw that on the graph, it passes the horizontal line test. So because it's one-to-one, what that means is this. It means if these two y values are the same, if 5 to the 2x is equal to 5 to the third, right? If those y values are the same, then the only way those y values can be the same, because it's one-to-one, is if the x values are the same. So because this is a one-to-one function, because it's a one-to-one function, we can make this next step. These y values are the same, so that means that the inputs 2x has to equal 3. I can discount the bases because it's a one-to-one function. And now I can solve this. I'm going to divide both sides by 2. That's fantastic. And I get that the solution is 3 over 2. And there we go. That's my solution set. I'm going to put it in some squigglies, and I'm done. All right, that's the basic premise behind solving a type 1 exponential equation where I can equate the two bases. So I would like you to look to exercise 6. So you've got 3 exercises. We're going to do one at a time. They have a gradual increase in complexity. So I would like you to please give exercise 6 a try. Just to give you a nudge, what base can I write both 4 and 8 using? 2. Yes, great. Right, so 4, you told me to use base 2, so 4 is 2 to the 2nd power. And then I'm going to put that in parentheses for the moment, and I'm raising, because that's 4, that's my original base, and I was raising that to the x plus 1 power. On the other side, 8 is 2 to the 3rd power. I don't need any parentheses because I wasn't raising the 8 to anything. Now what I have to remember to do, this is the power rule we reviewed a moment ago. I've got a power to a power. I've got 2 to the x plus 1 power. I'm going to multiply those things. And so I have 2 times x plus 1, which is 2x plus 2. Don't forget to distribute there. Probably the most common mistake made on the test on a problem like this. Okay, so just be super careful. Remember, you got to multiply all the way through. Is equal to 2 to the 3rd. And now here's the key step. It's an exponential equation. The exponential function is 1 to 1. So what I can do is if these two y values are the same, that means that those exponents have to be the same. So I can just reduce this to 2x plus 2 equals 3. I'm going to subtract 2 from both sides of this and get 2x is equal to 1. I'm going to divide both sides by 2, and I'm going to get x is equal to 1/2. There is my solution to that exponential equation. All right, if you didn't get that, it's okay. The next one is not a huge jump in difficulty level, so try exercise 7, please. Just a nudge. For 27 and 9, what base are you using for both of those? Okay, great. I loved all the voices. That's fantastic. Work it. All right, I'm going to get started. 27 is 3 to the third power. You just told me to use base 3, and then I'm raising that to the 4x. On the other side, 9 is 3 to the second power, and then I'm raising that to the x plus 2. So on the left side, that's 3 to the 3 times 4, or 12x. On the right-hand side, that's 3 to the 2 to the x plus 2 power, so that's 2x plus 4. Just going to make a pause real quick. Anybody got a question about where those powers came from? Okay, great. If you do, there's no reason not to, so I'm assuming that means you don't have a question. So now I'm going to equate the powers because the exponential is a one-to-one function, so that means that 12x has to equal to 2x plus 4. I'm first going to subtract 2x from both sides of this. So when I do that, I've got 10x is equal to 4. And then I'm going to divide both sides by 10 and get x is equal to 4 over 10. If you love decimals, make it a decimal. Be my guest on that. I'm just going to reduce this fraction. So my solution is going to be 2 over 5. And there's the answer to that problem. I've just got one more. So if you've got a question about this, get it out there. Verbalize it. The last problem is problem 8, and go ahead and solve that exponential equation. What base are you using for this one? Not 4. Yeah, it's going to be, I mean, you probably can do it with 4, but that's going to be it's going to be hard to write 1/2 as a base of 4. Okay, so on the left side, you've got 1/2. So I would recommend using 2 if you do it with 4 and get the same answer, or if you want to see where you went wrong, just see me after class. Okay, on the right side of this, I'm guessing that I would anticipate not a super lot of problems. 16. 16 is 2 to what power? How many 2's do you multiply to get 16? 4. Yeah, so 2 to the 4th, and then raise to the x plus 2. Again, I know sometimes it's a little awkward, but the 1/2 is 2 to what power? Yeah, we saw that when we did our graph just a few minutes ago on the front page. 1/2 is 2 to the -1 power. So I'm using base 2. And so now I've rewritten each of the bases on the left and right of the original equation in base 2. And so now I'm going to apply the power rule. So on the left, I have 2 to the -3 plus x power. On the right, I have 2 to the 4x plus 8 power. Since it's an exponential equation and the exponential function is 1 to 1, these two things can be equal only if their powers are equal. So I don't have to worry about the base because the bases are the same. If those bases are different, you have to employ a completely different technique, which we will talk about. We will talk about either on Wednesday or next Monday. So I'm gonna what I'm gonna do is I'm gonna subtract the x from both sides to get all the x's on the right. So when I do that, I've got 3x on the right. That means I've got to subtract the 8 to get all of my numbers on the left. So when I subtract the 8, I have negative 11 on the left. And then I'm going to divide both sides by 3, and I get negative 11/3. That is my solution to this problem. And there it is, solution set. Anybody got a question before I stop the video and we head on to the next section?